you gotta start somewhere. Okay, so a few other numbers. We've looked at that 500 exajoules per year, or 0.5 zetajoules. Another number to keep in mind, so if we just take that and turn it into power, this 17 terawatts is basically the size of the engine that runs humanity. You know, add up all the engines, all the power plants, all the solar panels, all the wind turbines. That's the size of our engine, 16.8 terawatts. Oh, yeah. There's that figure. That's the one. This is a fantastic figure too. So what they've done, and they've done a pretty good job of it. Typically, so when we get to summary 3, you're going to make similar plots. You already have at a smaller scale. When we get to summary 3, you're going to have a primary and a secondary axis. These authors have actually done a pretty good job of just plotting everything on one axis, because just as it turns out, the numbers are on the right order of magnitude. So the population is in blue, and these are all well-known statistics. The population of the Earth has been fairly well documented throughout the. Well, this is only 400 years, so no big secrets there. But we can see this exponential growth. So that truly is an exponential curve right there, and you can see that here we are at 7 billion. Here we are at 7 billion. That's the blue line, and then this is the other number we just looked at. So remember the 17 terawatts. This is the size of our engine. So our engine also kicked off a little bit here in the 1800s, and then you might say this is the nuclear age. I don't know if these authors talk specifically about what fraction. I don't remember. Well, actually, no. I think it was something on the order of 16 to 20% of all primary energy comes from nuclear reactions. France gets as much as 80% from nuclear, but this is a combination of nuclear energy coming online and just bigger machines to pull more coal, gas, oil out of the ground faster.
Greater efficiencies.
Yeah. Yes. Now, total energy consumption. Now, this number appears to be peaking. The green number is simply the red number divided by the blue number. So if we're up here at 17, we divide 17 by 7, and we're 2.5, something like that. So, and that's actually, it's energy per capita. So remember when we talked about solar, electric, PV energy, I said that an average North American household runs at about 1 kilowatt. Well, 1 kilowatt is right about there, 1/5 of the way up that line. This is about 2.5 kilowatts, and that's exactly where we are, because if we go back to these numbers, so all of a sudden these 3 numbers bring it all the way back to the human scale. So the 1 human power, that's about 100 watts. 100 watts. So we just took it to 200. We have 200, and I used to call that 20 techno slaves. You've got 20 human powers out there running for you, because you don't push your car. I'm not going to go out and start pushing that bus to get the people moving. It pulls us along. So there are 20, I'm not pedaling my computer right now to keep it moving. These are all just sort of, running in the background, these 20 techno slaves. And that's exactly where this 2 kilowatts comes from. So now, the next part is, it appears as if we have peaked. So, is that because there's less energy we can go after? Is it because we're all using LED light bulbs now? Is it because we're starting to carpool? What is it? Now, the answer is probably all of the above. But what we, in general, want to have happen moving forward is that the quality of life improves without wrecking the planet, right? So you would hope that this curve actually means we're more efficient, not that we're just simply running out, right? That's the hope there. Okay. Now, if you want to throw in an equation, you could start here. It'd be a good place to start.
What's omega stand for?
Omega stands for the end of energy. It's a calculation for like when it runs out. That's all it is. And so they've actually done this. Said there's your 3.6 joules per person per year. So that's your 200 megajoules times the number of days. You can work that out. And what they do is they plot it, ends the number of people on the planet. These numbers start looking even weirder and scarier. Because it starts. Well, yeah. So it starts again with the year, and this is again 2,000 years ago. So it's the same exact time scale we saw previously. And what it says is that 2,000 years ago, at the rate of consumption 2,000 years ago, we had 68,000 years of biomass left. And now we don't.
At a specific rate of consumption.
At that rate of consumption, right?
As the rate has gone up.
As the rate. So what's strange is this is time as a function of time. So omega is it's the time left. It's like how much time's left on the clock before the game's over. And what is this? 1750 or 1800. At that rate, we had 10,000. What's the flat spot?
Ice.
That's the plague. So that's when a third of Europe died. And so the forestry grew. You know, like, the engine stopped running. Now, what the authors then do is they come in and take a closer look. This is also why it's important when we do that summary 3 that we look at the linear, the quadratic, and the exponential functions, because now you can sort of see if you move to those quadratic and those exponentials, it allows you to get that curve in there. And it says, oh, are things getting better or worse? That's the whole point of doing summary 3.
And with the power of prediction, prevention.
Right. This is our look into the crystal ball. We're in a pretty cool place that we get to look, back in time and into the crystal ball. So now you see, you zoom in even further. We hit the year 2000. Like, whoopsies, 1,000 years of biomass left at the current. And these numbers actually match those worldometer numbers pretty well. If years to the end of gas, years to the end of oil, years to the end of coal. It's on the order of, well, depends.
I don't know what variables he used, but Stephen Hawking just pronounced that he believes the same thing. I think we have about 1,000 years left.
Okay, at the current rate. Now, but this is the current rate. And remember, a second ago you said, are these exponential or what are they? Well, the curve is improving. And again, the question is it because we're becoming more efficient, or are people doing without?
21, less people exploiting the surrounding environments.
Now, this is a pretty strong statement for a scientific paper. Normally, when you write a paper, you say, we hypothesize, or our conclusions might lead us to this, but you normally don't see a language quite that strong in a scientific paper. But there it is. And so they're like, I dare you to argue with me. Please, someone prove me wrong. Just please, somebody, tell me I'm wrong. Okay. No.
Being confident is good.
Okay, and then there's a few other, you know, history offers a mixed message about the, yeah. So, you know, go read your Jared Diamond. You know, he tells the bad news of Easter Island, tells the good news of Japan. Crash catastrophically, et cetera, blah, 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 blah. Yeah, so that's the paper.
That's cool.
That's the paper, yeah. A buddy of mine, the man who sent this to me, is one of three sons of the Corrick family, and the Corricks were the presidents of the timber industry back when Champion had its heyday here in Missoula. And I know one brother still in wood products. There's another one who's very successful developer and realtor here in Missoula. And then the other one is my personal friend, and he does a lot of PTSD meditation for people that have sort of dealing with issues. And so he's the guy that, you know, reads this type of stuff and sends it to me like, okay, Brad, what are we gonna do? Let's figure this out.
Meditate.
Yeah. Yeah. Do nothing at all.
Don't panic.
Yeah. No, I think the point is to just, you know, look at the paper for what it is, and, you know, realize that it's. I don't know how you would argue with this paper. I mean, there's just mountains of data. I don't think their bibliography is exceptionally long, but
It brings to mind all of the different stories and ecosystems, labs, drivers.
yeah, 40. That's pretty good size. I'm trying to see if I recognize any of these. So Brown, he's one of the authors. Hall. Energy and the Wealth of Nations, Understanding the Biophysical Economy. That's a good one.
I think Pfeiffer before.
You have? Pfeiffer? Okay. Yeah. Communities and Ecosystems.
So, same thing with this one, you want two different sources?
Yeah, two sources. So, you know, dig in here, see if something is interesting. So as you're reading through, like, oh gosh, I really like the sound of 20. Fragmentation and flow regulation of the world's large river systems.
So, in the actual paper, when they are stating facts and then they put numbers in quotations, that's what that is, they're referring to their bibliography?
Yeah, they use
Okay.
what's called the
So you don't
Vancouver
just
style.
pick one out of
Just,
that
yeah, grab one.
for whatever
Um,
quotes you're using in your paper.
Yeah, this is
That's what I did with the last
yeah,
one.
that's Running. That's Steve Running right there.
Oh, okay.
That's one of Steve Running's paper, 2004. 4 years of Mod 17 annual net production images. So that's, I mean, those are all housed right here, University of Montana.edu. Click right out there. So these are all as a result of some of the satellites that Steve Running and his colleagues, launched decades ago.
What does GPP stand for?
I had that at the tip of my tongue. Let's see, NPP.
Net primary production, is that global primary?
I think so. Let's check that out. The net,
Useful chemical emission.
it must be the gross, yeah.
Oh.
Gross and net, the gross is how much is there, and then the net is what doesn't get used.
Oh, really?
Yeah,
Okay.
yeah.
So net is kind of what's stored?
Exactly,
And gross
yep.
is everything?
Yep,
What's
that's
used.
yeah, so you could think of that, gross as the 2 zetajoules, and the net, after we've used a quarter of it, is the 1.5. That's what I think of that.
Back when you mentioned the 16.8 or 17 terawatts is the human engine, does that include both technological and metabolic energy that we consume?
No, that's just the technological. The 17 terawatts is just tech. Yeah, it's just tech. And obviously a lot of that goes into, farm equipment, which goes into feeding us, so, but it's just, our caloric consumption is 5% of our tech consumption, so. All right, well, that's all I have. Anything else? So,
Oh, we gotta get to the library.
get to the library, read this paper. It's not that long, it's like 6.5 pages, it's shorter than most. The figures are very poignant. It's published in the Proceedings of the National Academy of Sciences. Does not get much more authoritative than that. So, enjoy.
There's got quite the argument.
Yeah. Yeah.
No fooling there.
I'm not gonna worry about it. I was pretty much decided I'm not gonna worry about the big community recently, last couple weeks. It's a
Oh,
good feeling, actually, 'cause
and
I'm
if-
like,
Yeah. If you
I'm trying to
want.
enjoy my life.
Well, yeah.
I'm not bailing out, but, it's not gonna worry.
Well, no need to traverse the mountainside when there's a pathway leading up or the potential path to build. It's all about leaving behind a trace, a legacy for others to follow so that they might not make the same mistakes. that
Right? Because our
others
lifespan's
have.
pretty short, like, I can't spend that whole time worried about enough years in the future.
If-
It's the
And I-
nature of sustainability.
Yeah, and I actually dive into it in a little more detail in this talk. You'll see, I spent a lot of time in this talk that I gave in Billings a couple years ago talking about this paper, so
Or you need audio.
it's okay.
No?
Okay, thanks everybody. See you Thursday. We'll start in on chapter 4.